So today's topic is chirality. What this is a very strange concept. Chirality is really talking about molecules that can rotate plane polarized light. We say that a molecule that can do that can rotate plane polarized light, is chiral. And what we really mean is that the molecule is handed in some sense, that there are right-handed versions of molecules and left-handed versions of molecules. Because of the orientation of atoms in space, those molecules cause the rotation of the plane polarized light. This concept that there's arrangement of atoms in space around a central atom usually implies that we have a stereocenter present. There are ways of getting chiral molecules that don't contain stereocenters, but broadly what that means is that most molecules that are chiral have at least one carbon that has 4 different things attached to it, and that spot is a stereogenic center. It can either curl one way or it can curl the other way. Why does chirality matter? Well, fundamentally because our bodies are chiral. Every single one of the amino acids that makes up your proteins that keep you alive is the left-handed version of the amino acids. And so the molecules that make up our bodies are chiral. They're left-handed or right-handed, depending, and that influences the way they react with another molecule. So for example, if we have this molecule, which you can see is a glove that is made for a left hand as opposed to a right hand, you know that trying to interact the glove with the left hand is going to work. This is, in fact, the way this is intended to go. Meanwhile, try to put that same glove on your right hand, and it just doesn't behave the way it should. And broadly speaking, that's why we care about chirality. Our bodies are chiral, so they interact with chiral molecules differently. There are certain chiral molecules that are useful to our body, and other chiral molecules that are simply not. For example, if you are eating an artificial sweetener, aspartame, one of the reasons why it's an artificial sweetener that doesn't provide any caloric value to our bodies is it uses the wrong stereogenic center of the amino acid. It uses the right-handed amino acid instead of the left-handed version. So our body doesn't recognize it as food and it just passes right through. So when we have molecules that are achiral, say a glove like these blue lab gloves that doesn't matter whether it's your right hand or your left, you can put it on your left hand just fine, or I can take it off and put it on my right hand, and it works in either cases. And that's really how chirality works as well. If you have achiral molecules, it will interact just fine with the chiral enzyme. But where you potentially have trouble is when you try to use a chiral enzyme and a molecule that is itself chiral. It can either be matched well or mismatched. There are all sorts of objects in our daily lives that are chiral. If you are a golfer, you can immediately recognize that what I'm holding in my hand is a right-handed golf club as opposed to a left-handed golf club. Any number of objects that we use absolutely all the time, if they have handedness, then they are chiral. Okay, so what defines an achiral molecule? Well, at the core of what it means to be achiral is to have a plane of symmetry. So most people, broadly speaking, are achiral because there's a plane of symmetry that runs down the middle. You could cut off my right hand and recognize it to be a right hand regardless of where the rest of me is. However, I have both a right hand and a left hand, therefore there's a plane of symmetry running right down the middle.
The thing that we will encounter the most when we are dealing with chirality and stereochemistry is a situation like this, where you have a molecule that really has 2 different possibilities that it could be. It could either be the right-handed version of itself, in other words, what we call the R enantiomer, or the left-handed version of itself, what we call the S enantiomer. The relationship of the 2 molecules is exactly that of the relationship between your 2 hands. They are mirror images of each other. You cannot superimpose your right hand over your left. In fact, if you were to walk into a room where a bunch of dismembered hands were lying on the ground, you would easily be able to tell by looking or by picking them up and feeling them whether you had a right hand or a left hand. They cannot be confused for each other. They curl in different directions. On the other hand, they're pretty darn symmetrical. They are mirror images of each other. If there is a single lesson to take away, enantiomers are molecules that are mirror images of each other, and they are not superimposable. Said another way, you can't put the 2 molecules on top of each other and have them be the same thing, although they are mirror images. This is, of course, as opposed to identical molecules, where they are mirror images, but then you can take and superimpose both molecules on top of each other. Again, your right hand and your left hand are mirror images of each other, and you can't superimpose them, but 2 of the blue nitrile gloves that we use in lab are absolutely mirror images and can be superimposed. Our hands are enantiomers. Those non-chiral, achiral gloves are identical. Here I'm showing you the same molecules again, and the hydrogen's this little white ball, whereas the fluorine is the small yellow ball, and then chlorine is the green ball, and then bromine is the red. And what you can see is that if the reds are aligned with each other, and the carbons are aligned with each other, and the fluorines are aligned with each other, that then the green ball will end up where the hydrogen is in both cases. These two molecules are not superimposable. Right now, it may not be easy for you to tell that they are mirror images, but when I showed you the same image in ChemDraw itself, these are the molecules that I drew. These are very clearly mirror images. When I show them to you in Chem 3D, you can see that they are not superimposable. Just for fun, what I'm showing you here is a space-filling model of the molecules as opposed to the ball and stick that I was just showing you. This gives you a hint of the relative sizes of, say, a fluorine atom, a chlorine atom, which is the green ball, hydrogens, which are white, bromines, which are red, and then, of course, the carbon is the gray underneath. So these are what the molecules look like in sort of a space-filling model. Here what I've tried to do is to reorient the molecules in Chem 3D so that you can more easily see that there's really a plane of symmetry here. The chlorines are opposite each other, the bromines are opposite each other, fluorines are opposite each other, the hydrogens are opposite each other. Said another way, these are the same molecules we were just looking at. If I reorient them relative to each other by simply moving them in space, you can see that they are mirror images. Just like before, you can see that they cannot be superimposed. Again, if there's a single lesson to be interpreted from this so far, it is that enantiomers are mirror image molecules that are right-handed and left-handed, that they cannot be superimposed, whereas molecules that can be superimposed are therefore identical. Mirror images that you can set down on top of each other are really the same molecule. So one thing you might be asking yourself is how I know that this is the right-handed version. How do I know that this is the left-handed version, the right-handed enantiomer, the left-handed enantiomer? And the answer is in the way that the groups curl around each other, same as your right hand curls, your left hand curls. We are going to assign each individual atom as having a different priority, and we're going to use the Kahn-Ingold-Prelog rules of priority, same as we did for cis and trans Z and E sorts of analyses, where the higher atomic number means higher priority. This, in essence, means that a hydrogen is always going to be the lowest priority group. You assign priorities for all atoms that are surrounding the central atom, which in our case is almost always going to be carbon, and you put priority 4 facing away from you. If you have an H, it's always going to be the H. So the H is facing away from us back into the plane of the page. So let me now go ahead and assign the priorities. Keep in mind, the heaviest atom is going to have the highest atomic number. So bromine is going to be priority 1, chlorine is going to be priority 2, fluorine priority 3, and hydrogen, again, it's always going to be priority 4. So let's assign those. So now I've assigned all of the groups. Again, bromine 1, chlorine 2, fluorine 3, and H, which is always the lowest priority, facing away from us. So there you have the assignments of the priorities for each individual enantiomer. And then this is the way the book does it, but if the hydrogen is facing away from you, you just see if going from 1 to 2 to 3 in priority is clockwise or counterclockwise. And if it's clockwise, then you have a right-handed molecule. You have the R enantiomer. Again, as long as the hydrogen is facing away from you, if you move from 1 to 2 to 3 clockwise, this is right-handed. Obviously, over here on this side, what we have is the left-handed version of the molecule because, again, with the H pointing away from us, this curls the opposite direction. It's counterclockwise. You go from priority 1 to priority 2 to priority 3 in the counterclockwise direction. If that's true, then this is left-handed.
So I wanted to redraw the molecules again and walk through this exercise again and translate it for you into these models as well. So what we have here is the fluorine is blue, chlorine green, bromine red, hydrogen is the white ball. So anyhow, that is the molecule right there on the left-hand side. And then, of course, this should be the molecule on the right-hand side. Bromine toward me, fluorine up, green coming towards you, hydrogen back away. And again, as I just demonstrated it on the computer, when you have the priorities as follows, where the heaviest is 1, 2, 3, and then the hydrogen pointed back into the board is 4, then you can decide whether it is right-handed or left-handed according to the book. And the book would say, if you go in the direction from 1 to 2 to 3, and you are going clockwise, this is R. Whereas, if you go from 1 to 2 to 3 counterclockwise, then this is S. And that is very, very useful as long as the hydrogen is pointed back away. So if the hydrogen's pointed away, then this is really easy to see. Hey, this is going to be counterclockwise, and there you have it. But if we rotate it around the other way, then the book's description of what you need to do is that you need to have this whole thing flip. So let me draw that out for you. So I have redrawn the molecule, and all I did was rotate it in this direction so that now the hydrogen is pointed toward you. So the hydrogen is toward you, the chlorine's back away, and so on and so forth. So according to the book method or any other standard method of assigning stereochemistry, what you would now do is say, well, I go from priority 1 to priority 2 to priority 3, and this is going clockwise, but though that would be R, since the H is in the front, we need to flip that. This is still S. I am not a particularly large fan of this way of doing things because you either need to pick up the molecule and rotate it so that the hydrogen is back, or it needs to be so that the hydrogen is forward. In fact, I'd much rather do a different way of assigning priority, and that is to use my right hand. Something rather similar to the right hand rule in physics. So the way this works is I will either line up my thumb toward the H or away from the H, and this will work. So again, let's look at priorities. Bromine, chlorine, fluorine. So what I need to do is have my fingers curl, so I put my hand directly on top of the bond going from the carbon to the bromine, and then I curl my fingers toward 2. And when I'm doing that, you notice that my fingers curl from 1 to 2 to 3 as the priority, and my thumb is pointed away from the hydrogen. This is S. Trying it with R, I'm going to show you that we're going to curl my fingers from, now, red to blue. That's not working. Instead, I curl my fingers from red to green, and my thumb is now aligned along the carbon-hydrogen axis. So, if my right hand is working, if I can curl my fingers on my right hand from 1 to 2 to 3, and my thumb is aligned with the H, then this is R. If, on the other hand, when I curl my fingers from 1 to 2 to 3, my thumb is aligned away from the H, then this is S. Or if you prefer, if your right hand works, it's R. If it is your left hand that works instead, then this will be S. Which method you choose to use is entirely up to you. The advantage of using the right hand method to do it is it doesn't matter where this H is. I can always find a way to align my hand either toward it or away from it and see, oh yeah, in fact, this is S. My fingers are curling from red to green. My thumb is pointed away from the H, therefore this is S. While I have the models up here, what I'd like to illustrate is that if you swap the position of any two atoms, you change the stereochemistry. So again, right hand rule here will say my fingers are not curling from 1 to 2. Now they are. My thumb is pointed away from the H. This is S. So if I were to swap the position of any two atoms, then this should now be R. Said another way, my fingers should now work. I curl from red to green, my thumb is aligned with white, therefore this is R. Again, swap any two atoms, and what you are doing is flipping the stereochemistry. Swap any two of these, and you have swapped from one stereochemistry, one enantiomer, to another enantiomer.
So you may be wondering now what happens if you go to assign priorities and you find that there is a tie. Well, the answer is really simple. That means that you have an achiral molecule. It means that the possible stereogenic center that you are considering, this carbon atom, is not in fact a stereogenic center. And that's because in order for something to be chiral, in order for it to have a stereogenic center at that position, then you must have 4 distinct things bound. So this particular halogenated molecule that we're looking at has a carbon with 2 hydrogens bound to it. Therefore, there's a tie in priorities. There's only 3 unique things bound, of bromine, of fluorine, and then 2 hydrogens. Therefore, it's not a stereogenic center. Therefore, this molecule is not chiral. So to sum up what we've talked about so far, if you have non-superimposable mirror images, then you have enantiomers. If you have the possibility of non-superimposable mirror images, you almost certainly have a stereogenic center. That is a carbon that has 4 unique things bound to it. However, if you have a carbon that has 2 of the same thing bound to it, almost always that means you can find a plane of symmetry. In this case, the plane of the page itself is the plane of symmetry, where the fluorine and the bromine and the carbon are bisected by this plane and the 2 hydrogens are reflected in that plane. Therefore, this molecule is not chiral. It does not have a stereogenic center. This carbon only has 3 things attached. And just to help visualize it a little bit better, I will now put it into Chem 3D so I can rotate it so you can see there's the plane of symmetry that I'm talking about right here. 2 hydrogens, therefore, are on both sides of the plane of symmetry. Any molecule that has a plane of symmetry is always going to be achiral. It will not rotate plane polarized light. So, chirality means the ability to rotate plane polarized light. Any plane of symmetry within the molecule makes the molecule achiral. However, if you have 4 unique things attached to a single carbon atom, then that creates a stereogenic center that creates a center of chirality. And molecules that have centers of chirality are quite likely to be chiral. Although again, if you can find a plane of symmetry in those molecules, then all of a sudden they are achiral. We'll talk about that more in the next video, which is on diastereomers.